The time has come. You are preparing to become the first human to venture into a black hole, leaving behind your space colony of 740 individuals, which will alter its trajectory to settle on another distant planet. As you ready yourself, you are faced with an expanding black hole, its inner workings shrouded in uncertainty. But soon you shall uncover the truth. The challenge in comprehending black holes arises from the intricate task of envisioning a fluid space-time fabric. Space and time are not separate, rigid entities. They constitute distinct manifestations of a unified construct. This construct, known as space-time, is a malleable canvas upon which all universal events unfold, manipulated by the presence of masses that warp and twist it. Imagine if the stage upon which you stand bends and twists, and as you endeavour to move within it, what transpires? You are compelled to travel in alignment with the stage's curvature. Or, as the renowned physicist John Archibald Wheeler eloquently stated, matter tells space how to curve and space tells matter how to move. Within this framework, there exist two avenues to grasp black holes. The first involves understanding black holes as ordinary physical entities. When stars around 20 times the size of our sun exhaust their fuel, they release an immense explosion known as a supernova, expelling approximately 85% of their mass into the cosmos. Only their cores remain. These cores can retain a mass in the millions of trillions of kilograms. However, when their fuel depletes, the overwhelming gravitational force causes this substantial mass to collapse in on itself at an astonishing rate. Consequently, if the remaining core's mass is at least 3 times that of the sun, it undergoes this rapid inward collapse. Ultimately, an immense mass accumulates within a minuscule volume. Consider the vast mass compressed into such a diminutive space. Prior to transforming into a black hole, the radius of stars with masses over 20 times that of the sun is usually tens of times larger than the sun itself. Consequently, their density approximates that of the sun. Nevertheless, the core left behind after the demise of such a star, with a minimum mass of 3 solar masses, contracts into an area just a few kilometers across, a stark contrast to the sun's 696,340 kilometer radius. For instance, the black hole Giroux-Hankstein 55, exceeding the sun's mass by 5.5 times, boasts a radius of merely 16 kilometers. Yes, just 16 kilometers. Contemplate the feat of compressing such an immense mass into such a minuscule volume. This endeavor results in the space-time fabric bending to absurd degrees. This propels us towards the second approach to understand black holes. Rather than perceiving black holes as celestial bodies akin to stars or planets, envision them as ruptures in space-time, a rupture where a segment of the universe is severed, an anomaly that emerges within the very structure of space-time. And you, on the brink of entering this anomaly, will be the first to tread within. What do you anticipate will befall you? To comprehend, we must dissect the black hole into 2 components. Firstly, the physical singularity believed to inhabit the black hole's core, a minute point where the collapsed core of the progenitor star resides, akin to a void. We shall delve into its nature and why its existence is postulated shortly. The second facet is the pitch black sphere that greets, or rather remains unseen, when one gazes upon a black hole from the exterior, a void where nothing resides. This is termed the event horizon. Given our impending passage through it, let us explore the essence of the event horizon more closely. Normally, we have 3 spatial dimensions in which we can freely move: up, down, left, right, and forward, backward. However, black holes bend the space-time around them to such an extent that all 3 spatial dimensions begin to point in the same direction, toward the center of the black hole. So whether you try to go right, up, or backward, it makes no difference. Just as we cannot escape tomorrow, this place becomes one where you can't escape a physical singularity. Hence, photons that fall into a black hole, even though they travel at the speed of light, cannot escape it. This is why someone observing from the outside sees the region beyond the event horizon as a pitch black structure. This is because no photon from inside can reach our eyes or telescopes. It's quite remarkable, isn't it? For instance, when you reach a distance of 1.5 times the radius of the black hole, you enter a region known as the photon sphere. This is where photons, which normally take the shortest path between 2 points, end up orbiting around the black hole. Yes, the space-time around the black hole is so curved that even light can loop around the black hole's orbit like a planet. Once in this region, if you were to momentarily stop and look to the side, you could see the back of your head. This is because photons that reflect off the back of your head could loop around the black hole and reach your eyes. However, beyond this photon sphere, there's only one more stop: the event horizon. After reaching this horizon, your experiences vary depending on the size of the black hole. Hence, you must choose carefully which black hole to venture into. If you were to jump into a very small black hole, you could perish without seeing much. This is due to the fact that a black hole's event horizon size is determined by its mass. Thus, the smaller the black hole, the smaller its event horizon. Here's a little tip. To roughly calculate the radius of a black hole's event horizon, you can multiply its mass by around 3 in comparison to the sun's mass to get the size in kilometers. For instance, if the black hole is about 50 times the mass of the sun, its event horizon would be around 50 times 3, or around 50 kilometers. If you were to attempt entering a black hole with just a few kilometers in radius but carrying trillions of mass, you'd face a dreadful demise before getting too far. As you diligently approach the small event horizon of the black hole, you'll have already come dangerously close to its central singularity. When you get this close to the singularity, even your height of 1.5 to 2 meters can become problematic. The black hole starts to pull different parts of you situated at various distances with varying forces. For instance, if you were to approach the black hole with your feet pointing towards it, your feet being closer to the black hole by 1.5 to 2 meters than your head, would experience a much stronger pull. Your head would be further away, thus pulled with less force. These scenarios of varying forces are termed tidal forces. The tidal response around black holes begins to stretch you rapidly. In fact, it's more than just stretching. It's better described as spaghettification. You stretch so much that you become thinner and longer. As you elongate, one side of you becomes closer to the black hole than the other. Under these immense forces, you stretch like a spaghetti, eventually disintegrating into atoms. This dreadful process is known as spaghettification. So, if you wish to experience more action inside a black hole, it's better to consider entering supermassive black holes like the one at the center of our galaxy. In such massive black holes, for example, in black holes with masses at least 100,000 times that of the sun, the event horizon is much broader. This means the gravitational pull well inside the event horizon increases more gently, and even after passing the event horizon's boundaries, the gravitational forces allow you to explore the inside of the black hole without being torn apart. Let's say you found such a black hole and you're approaching it. As you get closer, the black hole starts to engulf you and your field of view completely. When you pass into the interior of the black hole from the universe itself, what would you experience? You wonder. Nothing. This is one of the most common misconceptions about black holes. The thing we call the event horizon isn't a physical object. It's merely a region where light can no longer escape, making it appear pitch black when viewed from the outside. And think of it like the shadow that falls on a wall. Thus, contrary to popular belief, someone falling into a black hole wouldn't sense that they've fallen into a unique void or entered a special place in the universe. People tend to believe that someone entering a black hole's event horizon would simply vanish or die instantly, but that's not true. Depending on the size of the black hole, after passing the event horizon, you'd continue falling toward the center of the black hole for minutes, hours, or even days, experiencing an increasing force that pulls you deeper. However, once you cross the event horizon, you wouldn't feel any that different. For instance, if you had a friend falling alongside you, you could continue having a normal conversation with them, or even play a game of table tennis as if nothing happened. You wouldn't feel any change in the passage of time. You'd just go on as if nothing occurred. occurred, the universe would gradually recede behind you, shrinking and eventually turning into a tiny dot. However, for someone observing you from outside the black hole, the scene would appear quite differently. They would see you approaching the event horizon, but never quite reaching it. Right as you were about to touch the event horizon, you'd appear frozen. Remember, time doesn't stop only when moving at the speed of light. It also slows down around very massive objects due to a phenomenon called gravitational time dilation. So at the event horizon where time dilation is at its maximum, an observer would see time stopping for you. Consequently, you'd seem frozen at that point. Additionally, as you approach the event horizon, your color would gradually shift towards red. This is because the photons you emit while passing through the increasing gravitational field would get stretched more before reaching an outside observer, causing the redshift effect. At the point where you ultimately froze, you'd start fading away slowly. This is because the photons you emit at that stage would stretch so much that they'd extend beyond detectable limits. Hence, an external observer wouldn't be able to witness you falling into the black hole. This is the most commonly misunderstood aspect of relativity. The fundamental truth that relativity shows us, but people struggle to grasp, is this: while we might agree on the events happening in the universe, how those events occur depends on the observer's speed and position. Grasping this concept fully is challenging, but if you truly want to understand how the universe operates, you must push yourself. Anyway, once you've passed the event horizon, there's no turning back. No matter what you do, you can't escape. And your speed doesn't matter. Pay attention. Even if you could travel at the speed of light, you still wouldn't escape the black hole. In fact, the harder you try to escape, the faster you'd approach your end, the singularity. Remember, the entire space-time fabric now points only toward that singularity. Every direction you think you could run in leads to the singularity. So whenever you attempt to move in any direction, you're actually getting closer to your end faster. Therefore, if you want to maximize the time spent within the black hole, there's only one thing you can do: stay still. In essence, your fate is sealed. All the directions and times you could steer toward in your future now point to a single place, the singularity believed to be at the center of the black hole. Let me explain why I've been mentioning believed to be at the center of the black hole. Because we can't obtain information from inside black holes. We can only predict what's inside them through the mathematical framework of general relativity. And let me tell you, this is no small theory. We're talking about a theory that has aced every test it's been subjected to. One of the most accurate theories humanity has ever witnessed. It could even go head to head with the theory of evolution, so to speak. For instance, Einstein's theory predicted the existence of black holes and what they should look like. Yet, when the first black hole was discovered, Einstein had already passed away. We managed to capture the first image of a black hole only about 5 years ago. So we were discussing a theory with an extraordinary predictive power, but here's the catch. These equations predict that within black holes, there exists a colossal mass compressed into an infinitely small point at the center. Let me remind you of a distinction I've made before between mathematical infinities and physical infinities. Mathematics can predict something to be infinite, but in the physical world, we've never encountered anything truly infinite because mathematics models an idealized world, whereas in physics, there are always approximations and rough solutions. For example, if you mathematically model the exact moment when a raindrop slips off the tip of a leaf and falls to the ground, you might see that the point where the leaf was attached becomes a singularity. This might suggest some kind of infinity. However, there are no singularities in the real world. If you could observe the raindrop's tiniest details, you'd see that even at the tip of the leaf, there are atoms that aren't infinite, but rather finite. This is why mathematical infinities don't necessarily mean there's an actual infinity or singularity. In fact, not everything mathematically predicted has to be physically real. Yeah, keep that in mind. Mathematics allows for countless different scenarios. The field of theoretical physics tries to determine which of the potential truths suggested by mathematics are worth investigating experimentally. In truth, very few people believe that there's an actual singularity at the center of black holes. Einstein's equations predict such a singularity not because there must be an infinity, infinity there, but rather because the equations of general relativity break down completely in the unbelievably tiny point at the center of a black hole. Just as we've seen before with Newton's equations failing to accurately describe the orbit of Mercury, a result of its proximity to a massive celestial body like the Sun. So this is what we quickly pass over as the singularity. When we're talking about something so tiny, the science of small objects, quantum mechanics, should come into play. But up until now, no one has managed to devise a theory that coherently merges quantum mechanics with Einstein's theory of relativity. As a result, we still don't precisely know what we should expect to find at the center of black holes. So what are the alternatives? According to some hypotheses, this center might be so warping the fabric of space-time in the universe that it reconnects to space-time at another point. And at that point, there might not be a black hole, but rather a white hole. A hypothetical celestial body that expels everything its connected black hole has swallowed. According to this idea, the atoms of a person shredded by a black hole could be regurgitated from a white hole at a completely different point in the universe. Unfortunately, we lack any observational evidence that white holes actually exist. To others, black holes might serve as gateways between multiple universes. This could potentially allow us to travel from one universe to another using black holes. But as you can see, all these wild ideas remain nothing more than speculations. The theory of relativity enables us to predict what will happen to you right up until you reach the singularity with astonishing precision. But the moment you cross into the singularity, we're in the dark about what happens. Perhaps someone from within must venture there to witness it firsthand. What do you think? That's how it is. I've saved the craziest and most thought-provoking truth about black holes for the end. All black holes can be defined by three simple properties: mass, spin or angular momentum, and electric charge, as black holes are almost always chargeless. So let's skip that for now. What remains are mass and the amount of rotation, and with these, it's possible to characterize all existing black holes. Of course, these two properties can take vastly different values in different black holes. Yet, there's a possibility for multiple black holes to have exactly the same mass and spin. And in this case, with precisely identical characteristics, there's no known way to distinguish one black hole from another. Yeah, there's something else in the universe that we know becomes indistinguishable when it possesses exactly the same values: subatomic particles. In other words, the most immensely massive objects in the universe share a peculiar commonality with the tiniest entities. What do you think this could possibly imply? We'll continue discussing these topics in upcoming videos. If you don't want to miss out, be sure to enable channel notifications. See you in the next video. Goodbye.